See, in the last session of electric and hybrid electric vehicles, we have started with the concept and architecture of hybrid electric vehicle. Okay, so we have seen many types, many architectures of hybrid electric drivetrains are available, right? We have seen series parallel hybrid, and complex hybrid network. Okay, so what we have seen in hybrid electric vehicle, we are available with two powertrains. Okay, so there are a number of possibilities that which powertrain will supply power to the load, and depending on that, we have classified into four different categories: series parallel hybrid, and complex hybrid. Right. So, in case of series hybrid electric drive, we have seen that two powertrains are connected in series, while in case of parallel hybrid electric drives, both the powertrains are connected parallelly to the transmission. They are mechanically coupled to the transmission. Okay, so we have seen the configuration of series hybrid electric drivetrain in the last lecture, and now in today's lecture we are going to see parallel hybrid electric drive trains. Okay, so this is nothing but a train. It is a drivetrain in which the engine supplies its power mechanically to the wheels, like in conventional internal combustion engine powered vehicle. Okay, and it is assisted by an electric motor that is mechanically coupled to the transmission. Okay, so the powers of the engine and electric motor are coupled together by mechanical coupling in this particular configuration. Okay, so the mechanical combination of the engine and electric motor power leaves room for several different configurations, and we will try to cover these possibilities in this particular session. Okay, so basically talk about this parallel hybrid electric drivetrain, then what we are available with is, you can see, one mechanical transmission is there, and this mechanical transmission is connected via some coupling. Okay, so this may be our coupling. Then there is one differential. So, yeah, let us say this is our two different wheels of my vehicle. Right, then suppose this is my mechanical transmission, right? And this is connected mechanically to this drive. You can say this is a final drive, or it is a differential, right? This is final drive and differential, and this differential is also connected to the wheels of the vehicle. Okay. Remember, this double line indicates the mechanical coupling, right? And this particular box is my mechanical coupling box. Okay. Now to this mechanical coupling box, we will be connecting our source of energies, right? So one source of energy is fuel tank, and another source of energy is our battery in this case. So battery will deliver the power to the electric motor, and fuel tank will deliver the power to the IC engine in this particular case, right? So we have IC engine over here, and then there is a motor right over here. Okay. So this motor and IC engine are connected to this coupling, right? So here also, this is my IC engine, and this may be electric motor, right? So now talking about the IC engine, if we talk about the IC engine is directly powered by a fuel tank, okay? Gasoline or diesel maybe. So here is what our fuel tank will be there. Okay? So this FT represents fuel tank. Right? And talking about the motor, okay, we are available with three-phase motor. It may be AC motor or it may be DC motor. And to get the desired speed torque characteristics from this motor, what we require? We require the control of this motor, and hence we will use one controller, power electronic controller, which is nothing but a motor controller over here. And this motor controller is supplied with our second energy source, which is nothing but the battery in this particular case. So this is my battery. They are connected in this particular fashion, right? So battery consisting of number of cells which are connected in series. And to charge these batteries, we will be available with one charger, okay? So we will have one battery charger over here. This is our battery charger, which can be charged externally from our supply, right? So this is the typical configuration. Okay, we can say this is configuration of a parallel hybrid electric drivetrain. Right? So this is the case which is going to happen. Now, suppose I am talking about the traction required. Okay, so in this case, what will be the flow? The traction will be provided by the engine. Okay, so if you consider the flow, then this will be the way in which our traction is going to be provided. Okay, this is first way. Second way, the battery may also provide the traction, required traction, right? So battery may also supply the load in this particular fashion, right? So you can see now we are available with two different sources which can supply the required torque, right? So this is advantageous in many ways compared to series hybrid electric vehicle. That is why we may find frequent use of this parallel hybrid electric drivetrain in nature. Okay, so this is first thing, right? This is about the delivering power to the load, right? So this red line indicates traction. Okay. Similarly, let us use one dashed orange line which indicates the charging of the battery. Okay. Why charging of the battery? Because whenever we apply braking, at that time, whatever kinetic energy of vehicle is there, we are using this kinetic energy of vehicle to charge the batteries. which is known as regenerative braking, right? So there are two ways in which you can charge a battery. The first one is we will charge the battery from the power which is developed by the IC engine, right? So this will be the first flow of power. Second, while braking, we will be able to charge the battery. Okay. So these are the two different things, right? So this is my source, which is nothing but electrochemical batteries, right? So this is the configuration of parallel hybrid electric vehicle. Okay. Now possibilities are only IC engine will provide the traction or only battery is going to provide the traction. And whenever we are going up a hill, at that time the combination of this engine and battery will provide the additional tractive effort required by the vehicle, right? So this is how this parallel hybrid electric drivetrain works, right? Now let us try to understand the torque coupling of this parallel hybrid electric drivetrains, right? So you can see from this figure that the mechanical coupling in this figure may be a torque or speed coupling. Okay, I am talking about this block. Okay. This particular block, this is mechanical coupling, right? So this mechanical coupling may be a torque or speed coupling, right? Now suppose it is a torque coupling, then this torque coupling adds the torques of the engine and the electric motor together, or they will split the engine torque into two parts. The first part is propelling and second part is battery charging. You can see, right? You can also charge the battery simultaneously and we can also propel the vehicle, right? So this is what happens. Okay. So let us try to understand this torque coupling first. Right? Then we will move on to the another coupling, which is my speed coupling, right? So we have this coupling, right? This is my mechanical torque coupling. So there are two possibilities of the torque. The first torque generated by IC engine, second torque generated by battery, that is electric motor, and we are getting some output torque over here. Okay. So let us call it first power is T in 1 omega in 1. Okay. Power P is equal to nothing but torque multiplied with the speed. And second power is T into omega into, and we are getting some output power T out omega out. Okay. So this is my torque coupling device, right? Now this conceptually shows a mechanical torque coupling which has two inputs, you can see. So one is from the engine and another one is from the electric motor. Okay. So the mechanical torque coupling outputs to the mechanical transmission. Okay. Now suppose we are ignoring the loss in this particular case, then what will be the output torque and speed, right? If you are ignoring the loss, suppose if the loss is ignored, then output torque will be, what will happen? It is nothing but the summation of the two input torque. Okay. So first one is, let us say T in 1, K1 T in 1 plus K2 T in 2. Okay. This will be the equation of the torque. And what about the speed? Omega out will be omega in 1 by K1 and should be equal to omega in 2 by K2, right? Let us call it equation number 2. So here I have mentioned the two particular constants K1 and K2, right? So this K1 and K2 are the constants which are determined by the parameter of the torque coupling. Okay. They are constants determined by parameters of torque coupling. Right? So this will be the case. Now, when we talk about this torque coupling, we have different torque coupling devices which are going to be used. Okay, so what the first case is, we will use the gearbox. Second case is we will use the pulley or say chain assembly. Then we can also use the shaft. Okay, so these are the commonly used mechanical torque coupling device, and in each and every case we will be able to find out this parameter K1 and K2. Okay, so there are variety of configurations in torque coupling hybrid drivetrains. Okay, they are classified into two shaft and one shaft engine. First is, okay, and each category the transmission can be placed in different positions and design with different gears, which results in different tractive characteristics. Okay, so an optimum design will depend mostly on the tractive requirement, engine size and engine characteristics, motor size and motor characteristics, etc., etc. Right? So as we have seen now, whenever we talk about the commonly used mechanical torque coupling, it may be with the help of gearbox, it may be with the help of pulley or chain assembly, or it may be with the help of shaft, right? So let us try to see this commonly used mechanical torque coupling device, as well as let us try to find out the values of this K1 and K2, which are nothing but the constants that are determined by the parameters of this torque coupling. Okay, so obviously for gearbox K1 K2 will be different, for shaft this K1 K2 will be different, right? So let us try to understand the first coupling device with the help of gearbox, right? So now I have gearbox and it is connected in this particular fashion. Okay, this is my second source. Okay, so this indicates the first input torque T in 1, let us say, right, and it will cause the speed omega in 1. Similarly, this is my electric motor which produces torque, let us say T in 2, and it will produce the speed omega in 2, right? Now these two coupling devices are connected with the help of gear. Okay, and it will give you some output over here, right? So this is my total torque output and speed. Okay, so power out will be equal to T out into omega out, right? Now let us say here the gear ratio we talk about is Z1, this is Z2, and here this is Z3. Okay, so this is my first possibility, and in this particular possibility, let us say K1 will be Z3 by Z1 and K2 will be Z3 by Z2. Okay, what are these Z1, Z2 and Z3? These are nothing but the number of two teeth. Okay, in one particular gear we are available with number of teeth like this, say. Okay, this may be one gear and rest of gears will be there, and then we will have one more gear over here like this. Okay, so whenever one wheel is having more gear and another one is having less number of gears, in that case we can either increase or decrease the speed depend on the gear ratio. Okay, so this Z1, Z2 and Z3, Z1, Z2 and Z3 indicates the number of tooth. Okay, tooth numbers of the gears, right? So this is first possibility, you can say. Now there is another possibility to take this output, right, with the help of gearbox only. Let us say, let us try to explore this possibility. The first input is my over here. Here is my second input, right? And these are connected mechanically via some gearbox in this fashion, right? Now what I'm doing, I'm taking output over here only. Okay, so this is our torque input 1, omega in 1. This is my power input 2, T in 2, omega in 2, right? And here two gearboxes are there, Z1 and Z2, and I'm taking power over here. This is T out, omega out. Okay. Now in this case, if you can see, now I am not taking the output in as in case of first case. Okay, you can see over here. Okay, I am taking the output common to the first gear tooth ratio at Z1. Okay, so in this case, if I talk about K1, then K1 will be equal to 1, right? And K2 will be equal to Z1 by Z2, where this Z1 and Z2 are nothing but tooth number of the gears, right? So there are two possibilities in case we are using our mechanical torque coupling device as an gearbox, right? So this was the first case we have discussed. Now let us try to discuss the second case where we are going to use the pulley, or you can say chain assembly. Okay, pulley or chain assembly. Right? Now this is quite easy. You have seen number of configurations of pulleys in control system. Also, we have seen this kind of mechanical systems whose transfer function was derived by us. Right. So here is my first device. Okay. So I will give some input over here. So my input power would be T in 1, omega in 1, right? And now I am connecting this particular case with another coupling over here having some radius, and then this is connected to my output assembly like this, right? And second input I am providing over here. Okay. So this is my motor input producing a power T into omega in 2, right? And this is also coupled via pulley, or you can say belt. Okay, so this is connected, this particular block is connected to the belt of input 1, and this particular is connected to the belt of input 2. Okay, so it may have some values. Say I'm talking about the radius of this pulley, right? So let us say the first pulley. Okay, the radius of first pulley is R1. The radius of second pulley be R2. This is my third pulley whose radius is R3, and this one is our fourth pulley whose radius is R4, right? And this results in the output power T out and omega out. Okay. So here we can see we are available with number of pulleys, right? And if you wish to find out the value of K1 in this case, then K1 will be equal to R2 by R1, and K2 will be equal to R3 by R4. Okay, so here this R1, R2, R3, R4 are nothing but radius of pulleys, right? So this is one typical configuration. Now another configuration is also possible where I am going to use only 2 pulleys. Okay, in this particular case we are using total 4 number of pulleys, right? Now let us try to reduce this number of pulleys to 2 only, and let us see what happens. So this is my first pulley having a radius of R1. Okay, this is my input 1, and here only I am taking the output, right? And then this is my second pulley having a radius of R2, which is coupled with the electric motor. Okay. So the input will be torque in 1 and speed will be omega in 1 over here. Similarly, torque input at terminal 2 would be T into and omega into, and this is rotating in this particular fashion, which is resulting in total output torque and speed. Okay. So here we have radius of first pulley as R1, radius of second pulley as R2. Okay. And if you can see, the value of K1 now would be equal to 1, because R1 divided by R1, it is going to be 1. But value of K2 in this case would be R1 divided by R2. Okay. So this is our values of K1 and K2, right? Where R1 and R2 is nothing but the radius of the pulleys. Okay. So this is another possibility of mechanical torque coupling device. Similarly, there is a third possibility, which is nothing but the use of shaft. Okay. So we may have seen frequent applications of this shaft. Okay, specifically when we talk about the electrical motors. We have seen number of electric motors directly connected to the shaft. So in this case now, whenever we are talking about the shaft, what is the advantage that the values of K1 and K2 will be equal to 1 in this particular case. Okay. So here is what my input is. Okay. And to the same shaft, I am providing the input 2 over here. Okay. So this is our torque input 1, which will result in omega input 1. And here we are providing torque input 2 and speed omega input 2. Now what is happening to this shaft? Whatever rotating fields are there, okay, this rotating, in this case, what is rotating part? Rotating part is the wheel of the vehicle. Okay, so the wheel of the vehicles are over here. They are connected mechanically to the shaft. Okay, so this indicates the rotor in our case. Okay, sorry, these are stator in our case, and rotor is the shaft only. Okay, shaft is rotating, right? So this indicates stator and this indicates rotor, right? So now we have provided 2 inputs to this particular case. First one is T in 1, second one is T into omega into, which will ultimately result in output torque and output speed, P in omega out. Okay. And what is the advantage in this particular case? The advantage is the constants K1 and K2 will have same value, which is equal to 1. Okay. So we are not providing any ratios, gear tooth ratios, or we are not providing pulley with different radiuses, right? So the parameter, constant parameter in this case would be equal to 1. Okay. So these are the commonly used mechanical torque coupling device which you may find frequently in parallel hybrid or series hybrid electric drivetrains, right? Now here I have told you that whenever we talk about this shaft coupling, you will find frequent application in shaft coupling, right? So this shaft have two particular categories. What are the categories? They are classified into two categories. What are these two categories? We have discussed is one is two shaft design. Two shaft designs and one shaft design. Right? So now let us try to understand this. What do you mean by this two shaft design? What do you mean by one shaft design? Okay. So to understand this, again we will try to draw a block diagram for this particular case, right? So I have one first transmission, let us call it transmission 1. Okay. Then I will have here second transmission, let us call it as transmission 2. Okay. So transmission 1 is pertaining to IC engine, right? So here is what our IC engine has been connected. Okay. And the IC engine is supplied by a gasoline fuel, and the transmission 2 is because of the traction motor over here. Okay, so this will be our electrical motor in this particular case, which is controlled by a motor controller. Okay, and this is provided, the power being provided by source of battery. Okay, so here is what we have generated, these two transmission 1 and transmission 2, right? Now this transmission, you can see one transmission is there, then there is a need of coupling. Okay, we are talking about the torque coupling right now, and we have seen three different types of torque coupling. First is with the help of gearbox, second is with the help of pulleys, and third one is with the help of shaft. Okay, so let us try to understand the two shaft configuration or two axle configuration, right? So what we are doing here, I am using two different axles. One is connected to transmission 1 and another one is connected to transmission 2, like this. Okay, this is my first shaft and this is second shaft. Right? And then these shafts are connected to the main drive, or it is also called as differential, right? And then these are differentials are coupled to the wheels of a motor. Okay. So this particular configuration is my two shaft configuration or two axle configuration, right? Okay, so here what we have done, we have used two transmissions. Okay, you can see one is placed between the engine and the torque coupling T1, and another one is placed between the motor and the torque coupling, that is T2, right? So these both transmissions may have single gear or multi gear, we don't know exactly, right? So here it is clear that these two multi-gear transmissions will produce many tractive effort profiles. Okay, so the performance and overall efficiency of the drivetrain may be superior to other designs because T2 multi-gear transmission provide more opportunities for both the engine and electric traction system to operate in their optimum region. Okay, and this design also provides great flexibility in the design of the engine and electric motor characteristics. Okay, but the two multi-gear transmissions will significantly complicate the drivetrain. Okay, if there are some advantages, there must be some demerits or disadvantages. Okay, so whenever we talk about the multi-gear transmissions, the drivetrain becomes somewhat complicated, right? Now here, in this case, suppose these transmissions are single gear transmissions. Okay, so the single gear transmission T1 and multi-gear transmission T2 may also be used. Okay, in previous case what we have discussed, T1 is also multi-geared and T2 is also multi-geared. Now another possibility is T1 may be single geared and T2 may be multi-geared. Okay, so in that case our tractive effort and speed profiles will be different. Okay, so in actual hybrid drivetrain, the maximum tractive effort with this transmission arrangement may be sufficient for the hill climbing performance of the vehicle. Okay, greater tractive effort would not be necessary due to the limitation of the tire ground contact adhesion. You can see. Okay, the use of this single gear transmission takes inherent advantage of the high torque characteristics of electric machines at very low speeds. Okay, and talking about the second, the multi-gear transmission. Okay, the multi-gear transmission is used to overcome the disadvantages of the IC engine speed torque characteristics. Okay, we have seen the speed torque characteristics both for the electric motors also and for the IC engines also, right? So what we have seen in case of electric and electric motor, we have seen in the electric motor that we are getting these speed torque characteristics, right? But when we talk about the IC engine, to get this particular shape, we have to use multi-gear transmission. Like first gear will give you these characteristics, second gear will give you these characteristics, third and fourth gear will give you these characteristics. So overall, we will be able to get these characteristics similar to electric motor, right? So it is advantageous for us when we are in the use of IC engines. At that time, multi-gear transmissions will be beneficial to us. Okay, so this multi-speed transmission also tends to improve the efficiency of the engine and reduces the speed range of the vehicle, in which an electric machine alone must propel the vehicle. So consequently, it will reduce the battery discharging. Okay, so energy will be reduced. Okay, now talking about the third possibilities. Okay, in the contrast to above designs, right? The third possibility is single transmission 1 for the engine and multi-speed transmission 2 for the electric motor. Okay, and this configuration is considered to be unfavorable design, right? Because it does not use the advantage of both the power plants. We may see whenever we are using the IC engine with multi-gear transmission, at that time it will provide us with the advantages, right? So whenever you are using the IC engine as a single gear transmission, definitely we are not using the IC engine at the maximum efficiency. So this particular configuration is not favorable to us, right? So these are the some of the configurations which we are going to use or which we can use in the case of parallel hybrid electric vehicles. Okay, of course there are multiple possibilities. Like you can say, we have seen right now two shaft configurations. Similarly, we may have some transmission from the single shaft torque combination, or we may have single shaft torque combination parallel hybrid electric drivetrain, or we may have separated axle torque combination of parallel hybrid electric train. Okay, so we are not going to see this each and every configuration. Okay, we have already studied the first typical configurations which is widely used. Now talking about the speed coupling. Okay, this was all about the torque coupling, which will provide us the output torque like this: K1 T in 1 plus K2 T in 2. Similarly, we should also know the speed coupling. Okay, so let us see what happens when we are coupling the speed. Okay, or what are the possibilities of this speed coupling. Okay, so the powers from two power plants may be coupled together by coupling their speeds. Okay, how? Simple. If we have one speed coupling device like this, then what we are doing? We are taking the power from the first power plant, we are taking the power from the second power plant, and then we will be getting some output power over here. Okay, so this is nothing but the speed coupling. It is similar to the torque coupling, right? So we are getting some output power, T out, omega out. Okay. The input may be T in 1, omega in 1, and T into omega in 2. Okay. So the characteristics of the speed coupling can also be described by the equations similar to the torque coupling, right? If we talk about the output speed, omega out, then omega out is given by K1 omega in 1 plus K2 omega in 2. Let us call it equation number 3, and torque out would be T in 1 by K1. It is equal to T in 2 by K2, right? Again here, K1 and K2 are constants which are associated with the actual design, right? Now, similar to torque coupling, we may have typical speed coupling devices also, right? So one is planetary gear unit, and the another is an electric motor with a floating stator, which is also known as transmotor, right? So we have two two typical speed coupling device, right? The first one is planetary gear unit. A planetary gear unit, and another one is the motor, electric motor with a floating stator, which is also known as transmotor. Okay, whenever you go through some research paper, you may find this word frequently, transmotor. It is nothing but the motor with a floating state, right? So there are two possibilities like this, and we will see each possibilities and the value of the constants K1 and K2. Okay, so talking about the planetary gear unit now. So we will be available with a unit of gears like this. You can see. Okay, so this is my first part, right? These are also connected internally like this. So this indicates the first part, this indicates the second unit, and this is the third unit. You can see we have total 3 units, right? If I try to draw the side view of this, then we may find, okay, so this is the first unit. Okay, so we may have our first circle or a gear having a radius of say r1, right? Then we have this second coupling over here, like this. Similarly, this is our center line, and this is second coupling is the outermost coupling, like this, the outermost unit having some radius of say r2, and this radius is r3. Okay, so we have total 3 different units. Okay, now the first unit, let us this. Okay, the speed being omega 1, torque production being T1. Second unit, generate speed of omega 2 and torque 2. And third unit, omega 3 T3. Okay, so these are my 3 different speeds generated by 3 different gear units. Right, now we are interested in the speed of unit 3, which is our output. So we are talking about omega 3 in this case. Okay, so omega 3 would be r1 divided by 2r3 omega 1 plus r2 divided by 2r3 omega 2. Okay, and if I talk about T3 is 2 times r3 by r1, and T1 is 2 times r3 by r2 T2. Okay, and talking about the K1 is r1 divided by r3, but there are 2 units, so 2r3, and K2 will be equal to r2 divided by 2 times r3. Okay, so this is how we will be able to get the values of K1 and K2. Okay, so we are using gear unit. In this particular case, we have used total 3 units. Okay, and this is how we will be able to calculate the constants T1 and T2. And then there is another possibility, which is nothing but the electrical motor with a floating stator, right? So what do you mean by this floating stator now? See, we have a 3-phase motor over here. Right? This is the shaft of the motor. Like this. Then this motor is protected with the help of some body. Okay, like this. Right? And it is being supplied by 3-phase supply. Okay. So this is a floating stator. You can see stator and rotor are different parts, right? So in this particular case, now if I draw the cross-sectional view, then what you may find that this inner part is my rotor part, and then there is a outer winding which is a stator winding, which is floating, right? And it is rotating in a particular direction, having a speed of omega s, generating torque omega t. Okay? So in this case, if I talk about the speed of the rotor, then omega r is nothing but omega s plus omega rr, and torque will be equal to torque generated by the stator. Okay, so here this omega rr is the relative speed. Okay, it is nothing but the relative speed of the rotor to the stator, right? So up till now, whatever motor configurations we have seen, what we have seen is stator is a stationary part and rotor is the rotating part. Okay. So we will give some supply voltage to the stator, and because of this, whatever torque is produced, because of this torque, rotor will rotate in a particular direction. Now this transmotor is a motor in which we are providing the floating stator. Okay. So stator is also rotating along with the rotor. Okay, so I am talking, if we talk about the resultant speed, then resultant speed will be the speed of the stator plus the relative speed of the rotor with respect to stator, right? As we have seen that rotor speed, in case of three-phase induction motor, we have seen that the speed of the rotating magnetic field and the rotor speed may not be equal, because if that speed is equal, then there is a problem of magnetic locking, right? So in this case also, rotor is rotating, but stator will be rotating at different speed. Okay, so there will be some relative speed. So that relative speed is added to the speed of the stator. Hence, we are getting our resultant speed in this particular case. Okay, so these are our two possibilities of the cases, right? So here, this rotor and the air gap through which electric energy is converted into mechanical energy. Okay? So the motor speed in common terms is nothing but the relative speed of the rotor to the stator. And because of this action and reaction effects, the torque action on the stator and rotor is always the same, and it results in the constants K1 equal to 1 and K2 equal to 1. Okay. So just like the torque coupling device, the speed coupling units can be used to constitute various hybrid electric drivetrains. Okay. So we may see the hybrid electric drivetrains with speed coupling of planetary gear unit, or we may have hybrid electric drivetrain with speed coupling of electric trans motor. Okay. So these are the possibilities in which we will be able to connect the speed coupling, right? So this is all about the speed coupling and torque coupling, which are going to be used for hybrid electric vehicles. Okay, there may be some possibilities, but some configurations which we are not going to see, because the configuration will be same like this. Okay, here we have used the two transmission, that is two shaft axle. Now this is my coupling unit, right? So this coupling unit may be replaced by speed coupling or torque coupling, right? So this is how you can explore the possibilities of different configurations, right? With the help of this planetary gear unit, or with the help of this electrical motor with a floating state, right? So we shall stop here. This is all about the hybrid electric vehicle. Now time comes to talk about the propulsion unit, which is of our prime interest. Okay, so from the next lecture, we will start with the electric propulsion unit, the different electrical motors which are going to be used, or they are used in different electric vehicles as a propulsion unit. Okay, so we'll see the construction and characteristics and drives used for these particular motors from next lecture, right? Okay, if you have any questions, then you can ask.